Of how this working on this will be, I'm going to get you started, but it's really meant to be kind of independent, figure it out on your own or with your math amigos. So I'll get you started, and then you're rolling. All right? So, what's that? 82. Oh, 82. You still have 82? Keep it to Monday. Although I have the key for 82 posted, and I will have 83 posted, so use those so you can minimize questions on Monday. All right, here's the deal. Back about 1780 or so, there's this Italian guy, really physicist, and there were some questions in physics he could not answer because the math didn't exist to answer them. Rosati, I think. Okay, but at any rate, he makes these combination functions called that really amount to hyperbolic trigonometry. Now, the trigonometry name is a little bit of give and take. In one sense, it's really misleading because it has nothing to do with triangles. It has nothing to do with angles. And so it's really not like trigonometry in that sense. However, it is like trigonometry in a million other senses. There are identities. The derivatives are very similar. The behavior, in a lot of ways, in integrals is very similar. So you'll see why they went with trigonometry because there is so much parallels to trigonometry. Right? So here's the two big ideas that he came up with. They come from combinations of the exponential function. If you take e to the x minus e to the negative x over 2, he called that the hyperbolic sign. And it's written that way, at least in America. Although I guess in Europe they would write it SH, and they would write normal sign SC for circular sign versus hyperbolic sign. Crazy, but I've never done math in Europe, so I can't really say if that's true or not. So this, though, is pronounced, at least every professor I ever had, cinch. Okay, you would read that as cinch, although the H stands for hyperbolic. Sine hyperbolic, pronounce it cinch. E to the x plus e to the negative x over 2 is hyperbolic cosine, and that is cosh, not kosh, cosh. Okay? All right. So you make these combinations of exponential functions, and keep in mind it's exponential, it's not trigonometric. So when I say sine of 2, it's implied that that 2 is an angle. That's 2 radians, right? If I say sinh of 2, that's an exponent. That has nothing to do with any angle. It's not an angle, okay? So have that in mind as you go. Let's go into a few similarities then, why they call it trig. One is there's a huge identity. Cosh squared minus sinh squared equals 1. It's a little different because it's not sine squared plus cosine squared equals 1. I would like you to prove it. Prove it for me right here. If you read, I think if you read, this will go pretty well over the course of the period. However, if you don't read well, you will not find this informative at all. Okay? Feel free to work with your mathematics too as you get stuff done. The goal is to prove that's true by going to
Yeah. How do you start?
Start by factoring. It says right there.
So cosh minus sinh
Cosh minus sinh. Now you're talking.
times cosh plus sinh.
There you go, boy. That's what I mean by start by factoring. Now go to exponential.
Yeah, and then you send an exponential.
Me too. I have no idea.
Like cosh is like, okay.
I guess it doesn't sound good to say sin huh. Or sin sign huh. I don't know. They didn't ask me for my input.
They should have.
Yeah, they should have.
Now.
It's English.
So then you just get
Yeah.
Will this be on the AP exam?
This is not an AP exam topic, BC or AB. However, it is on pretty much every syllabus, college syllabus I ever saw. Calc 1 or Calc 2. So it's important that you've seen this, especially if you're going on. This is more of a science application. It doesn't have a lot of, has no business application that I know of. But it's definitely useful in science, and I'll talk about a few.
I gave up.
No. I just realized that like one side
X minus X.
Okay, so you get somewhere along the lines to e to the negative x times e to the x, which you can either say is e to the 0, which is 1, or 1 over e times e, which is 1. Either way, it's... Yeah? Okay, moving on then, a few more together items, and then we'll let you to it. Are you ready to move on? Can I move on? Okay, so why? Okay, so great. It's these exponentials, and it's got a trig connection. Why they call it hyperbolic? It's hyperbolic. This is kind of cool. This I finally made the connection on today, so thankfully I'm still learning. Okay, so if you start with sine squared plus cosine squared equals 1, and you let x equal cosine t and y equal sine t. Let's pause there and go back to trig. Why would you do that? Just because it's fun? Well, no. Cosine is, by definition, adjacent to hypotenuse, right? And if you put it on a unit circle, then the adjacent side is x. And if it's the unit circle, the hypotenuse is unit 1. Okay? So that would imply then that from that it follows x equals cosine. So it's not like that was just pulled out of thin air. There's a reason for that. X equals cosine, y equals sine. If you make that substitution, then it becomes y squared plus x squared equals 1. And that yields the unit circle. Okay, so points on the circle being any point x, y could also be represented by cosine, sine. Which, when you do all those unit circle quizzes, that's what you're getting. Yeah, the cosine and sine at that end, right? Okay, now in a similar fashion, but without the triangle connection, there is no adjacent to hypotenuse here. There's no triangle. Okay? But if you let the same kind of substitution happen, x equals cosh and y equals sinh, then you get something like x squared minus y squared equals 1. Now that's not a circle, that's a hyperbola. And it's a sideways opening hyperbola where any point x, y could be represented or considered the cosh value and the sinh value. But again, that t is not a name. All right? That's why they call it hyperbolic trig, because the basic identity boils down to a hyperbola equation rather than a circle equation. Right? Well then, off you go. I will say this. Tyler Brown and I had a little discussion about this. I had a discussion. So all of our discussion started this way. He says, on the internet I read blah, 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 blah. And then I don't read the internet, so I don't read stuff that I read in college. Okay? So I was never taught any abbreviation but sinh and cosh. And if you wanted to say hyperbolic tangent, you said hyperbolic tangent, hyperbolic cosec, hyperbolic cotangent, and so on. Okay. He says on the internet they're called tanh and sech, or I never heard that. I never heard that. So take it for what you will. If you want to make up your own name, sech, ha, whatever. I guess I'll eventually figure out what the heck you're talking about, but the right way, the safe way to say hyperbolic secant. Hyperbolic secant. I know it's not mistake, but there. The rest of it should be pretty self-directed until you get to the graph side, and then I'll probably bring you back and talk about it. But go ahead and start working on it. I encourage you to work together. Yes. Good.
Right cheese.
That's why he was like,
Done.
Does it save them or just
Figure their exponential forms out.
Take this, divide it by this. That wasn't my cinch over.
I guess my directions were clear. I would like you to give me the exponential forms of the
So that means you put x minus over 2 divided by e to the x plus e to the negative x. So over 2. That just means you know how to so like, so then Kyle, did you cancel it out or no? Any of you don't think so. Over e to the x minus e to the negative x. It's just inverses, right? Sec, that'd be 1 over cosine. So 1 over e to the x plus e to the negative. Oh, 2 over, yeah, that's right.
What you do, people call it your program
Maybe actually 2 over
that's what I do.
x minus
I'm literally doing that right now.
inverse.
Wait, no, it's here, it's here, it's here.
Oh, hey.
Right there.
Like you said,
You just wait. Yeah, that's what you're correct.
Correct. Thanks,
I don't know, I think it'd be a job getting a bit of fans.
Ghetto calculator.
I like how you can hear it anyway else.
It's the negative 1.
You can do this without your calculator.
Why would you use the 1/2?
Oh, you go back.
Wait, yeah. What? I think you need to
I was like, wait.
Yeah.
Oh, isn't e the 1.77 something? So you could do like 1.3.
You're good at that. I'm lying. I'm a lying sacrifice.
Yes. I did. It's not right news. Oh, yes, I think it's supposed to be a negative. It would just be on the same.
That's what I did, yeah.
Oh, yes, so sorry, there's an error on the back. Could you turn the back real quick? Top column, it should be e to the x over 2 and e to the negative x over 2. Total typo. It doesn't matter, but I meant the second one to be negative.
Has to be the intersection one.
Oh, wait, no, that's it's over the right. It will just be on the other side of the road.
You just confirmed my hypothesis. I just called it out a little soft. I had a little Einstein got back.
Oh, believe, were we on the graphic side?
Yes.
Okay, I would like, this is important to me, it's part of the, sorry, it's drawback for you for having a geezer teach. I learned to graph this stuff without a graphing calculator. It's important to me that you can do that yourself. You can think your way through a graph without the calculator. By the way, a lot of calculus classes you're going to have in college are no calculator, especially at mine. So, let's think, shall we? E to the x over 2, what does it look like? Where's across the axis? 1/2. And it would still be exponential, maybe grow a little slower, but still look something like that, right? Okay, the e to the negative x, how would it go?
Same way above the x-axis.
Same way, but flipped across the y-axis like that, yeah? Okay. Anytime you do a combination function, this thought process would be the same thing you would do. What I'm about to show you would be exactly what I would do if I said graph this. I would say, okay, what does each do? Sine does this, x does that. So if I put them together, this wants to grow big, but it would have some waviness to it, and so it would look like that. It's that simple. You just put the two together, and you say, how do they combine? Now, this has a variable center line, right? Okay. So, this then, if I combine on the right, I'm combining huge positives with small positives, and I get huge positives, okay? In fact, it would be like this plus even a little more. It would be growing like that even a little more, right? So it would be here. At the origin, 1/2 minus 1/2. It'll pass through or touch the origin. Okay, on the negative side. Remember, I'm taking e minus the e to the negative x. So I'm taking solid minus dotted. Small positive minus big positive. Small positive minus big positive. Big negative. Okay? All right. So use that same thought process for cosh. I'll pause again once you have that. I'll give you 30 seconds.
We don't care. Wow. Thanks, God. You got it. I got it.
Ready?
That's cool.
Me?
It's not like I do. I'll say that was
Because on the right, if you did.
You made a terrible joke.
You're Mr.
You laugh.
Okay. All right. So on the far right side, what's big positives plus small positives? Bigger positives. So this side would grow fast. What's the y-intercept? 1, a half plus a half now, not minus a half, plus a half is 1. And on the left-hand side, big positives plus big small positives is big positives. Okay? And if that cosh is even, cinches are, just like normal. True. All right? Now, this actually is one of the big applications of hyperbolic trig. If I were to look at a telephone wire or any slack cable basically hanging, what kind of curve could I fit to that? Feels like parabola, right? And yet, I could not get an equation for a parabola that matches that. Not everywhere. I could get it so it would match here and here, but I couldn't get it so that it would match everywhere. A parabola doesn't fit that behavior. This does. Okay? A hyperbolic cosine curve is how you do where a slack curve lies in physics. It's also, by the way, if you try and fit an equation to the St. Louis Arch, not a parabola, hyperbolic cosine.
What was the original problem you created to solve?
I didn't say in the book I had, but just said he was a physicist too. It didn't really have one. It was like that. If you find more, I would love it. My math history textbook. At any rate, that's one of the applications. The other application is a calculus application. I'll get to that when you get to the end of the paper. Go back to working together. Yeah. Well, okay. Actually, generally, I know.
Oh, you have to use liquid
Other than being great math, I also like the X.
What are the words to evaluate? Oh no, James, you're so silly. What's the X? You have to do train roll, you silly thing. And then each the X. Minus the X over 0. That's after taking the derivatives, you have big over little, which would just be positive and negative. Each the X minus no, James, that's screwed up. I'm making that up.
Can we just say that, Nolan?
Yeah, just read it first. You just keep going back and forth and then get a difference with the limit. What is negative? My God, why? I didn't really get it.
It's pretty right.
Maybe
use the fractions, James.
Okay,
I'm so
so,
Taking my brain shorts.
all right, so what does the top go to?
infinity.
Okay, and what does the bottom go to?
Infinity.
And so it feels like L'Hopital, right?
Yeah.
Well, what happens if you do lots of derivatives?
You just do the same thing.
You get nowhere, okay? Now, we really use L'Hopital when the two functions are different. That's where we get somewhere. However, that said, we can think our way through this. As x goes to infinity, what does this go to? And what does this go to? And so now the issue is, all right, yeah, they're both going to infinity, but they're not different. They're the same. And so the rate at which they go to infinity would be 1. Okay? Imagine this numerical case if you're a number person. What's a billion minus a billion over a billion plus a billion? Isn't it pretty much just 1? You know what I mean?
So
Okay.
only in this case because they're going at the same.
Because they're the same function.
But otherwise, it's video.
Right. Now, there is one other thing. The reason I put this on is I'm not sure you understand a thing about calculus, and that is horizontal tangents aren't for both sides. Okay. You can have two totally different horizontal tangents on each side based on whether infinity and negative infinity behave differently. So please don't think that this is a horizontal tangent of 1 for both sides of the graph. It is. Go ahead and think on the second one. Think on the next one about which ones are going to 0 now.
Yes.
Oh my God.
Oh, I figured that out.
It's just kind of random sign that I
Yeah.
Oh my God. I was like very
Oh, yeah.
at least try that.
Oh, really?
Well, I am it, but I don't.
I just think it's so good. I'm like, oh, regular grab one.
I can do
Yeah, Why sound like
Well, if you take the limit of each of the x and try to fix it.
there's this lady that literally trains up.
Oh, look, there it is, right there. Look, because it goes to 1, how'd you get -1? I told you.
Getting recorded.
Negative.
Oh, even better. I hope they pick up. You can't hear it. You have to turn up the sound. I'm gonna get a.
Oh, it's going to 0.
Oh my God! Oh, clip right in front. It's going.
Yeah. I asked Miss Porter. She said she had the budget for it.
These are right. I was missing the part the whole time. It's brilliant. I wasn't looking at the sign of the exponents. I was just like looking at the face and I'm like, wow. That's pretty insightful. I think so.
What?
Oh, basic. Right there, it's pretty insightful. Observation.